Good morning. This lesson is going to be on graphs of square root functions. So in this unit, we really talked about radicals. We've talked about higher order radicals, the index, how to simplify them. We've gone into how to operate with radicals, multiplying, dividing, adding, and subtracting. We've looked at the connection between radicals and exponents, mainly that radicals can be written as exponents that are fractions. And now we want to get into what do square roots look like when we graph them. And you can graph like square root functions, and you can also graph like your cube roots and your fourth roots and so forth. But the most common kind of radical graph that you're ever going to see is a square root function. So this lesson is going to be partly exploratory. We're pretty much going to build a lot of tables and look at the graphs, and then we'll summarize the behavior of your radical graphs. In how you can take some shortcuts with that. And it'll be familiar to you from our study of other types of functions in their graphs. Originally, this lesson was completely exploratory, but that was from a time when we could have everybody on a graphing calculator and working kind of independently to graph stuff on the graphing calculator, and that's obviously not really an option this year. So before we dive into anything else, we need to kind of review a couple of terms that it's been a while since we've seen them. So we want to talk about the parent function. And just to review what a parent function is, the parent function is the simplest function in a family of functions. And we first talked about families of functions back with absolute value. And so in a family of functions, there we go. So that's what the parent function is. That's the definition. And some of the parent functions that we've looked at are like y equals the absolute value of x. And hopefully you remember that that is a V-shaped graph. And that was the one that we used to explore what are called the transformations on it. We've also looked at the parent function for quadratics. And of course, it's like the simplest kind of quadratic function there is, where you don't have anything multiplying, nothing being added, you don't have a linear term, and so forth. So when we're talking about a square root function, the parent function is the simplest function in that family. Like, how simple can you make it and have it still be a square root function? And the answer to that is this. You could have f of x is equal to the square root of x. That's as simple as it gets, and have it be a radical function or a square root function. If you're not comfortable with the f of x, you can always sub out a y for it anytime. I try to switch back and forth between them so that you can develop some comfort with both notations, but ultimately, like, you can always use a y instead of an f of x, and it won't be an issue for you. So what we're going to do is graph this by building a table. Now I want to toss an idea out to you before we get into that, and that is, we know that square roots are related to squaring. Okay, we do know that those two operations are related. We know that if we do 5 squared, we get 25, and we know that if we do the square root of 25, we get 5. And that squaring and square rooting are operations that undo each other, okay? That we've established, like, when we talked about what square rooting is. So it stands to reason, okay? Or it would make sense if the square root graph was related to the x squared graph, like the square root of x and x squared graph, which of course is the parabola. Okay, now we don't expect the graph to be a parabola because that's the graph of a quadratic, but we know that squaring and square rooting are related operations. So it would be logical to think that the graph of square rooting would somehow be related to the graph of squaring, which of course the graph of y equals x squared is a parabola. So I just want you to keep that in mind as we're building our table and plotting those points. We don't really know what this graph is going to look like, but we're expecting it to be related to the graph for a quadratic. So on my next slide here, I have a coordinate plane set up, and I have the parent function y equals the square root of x. And what we're going to do is plug in some numbers for x and see what we get out for y. Now I'm going to start with, what will we start with? Let's plug in like x equals 0. We'll do x equals 1. We'll do x equals 2. Now, I know in this that I'm taking the square root. So let's kind of think of some numbers that are nice and easy to take the square root of. Like I could do the square root of 4, okay? And the square root of 9. That would be good. And those numbers are all positive. So let's throw in like a negative. Let's do like a square root of negative 1 and maybe a square root of negative 4. Okay? And you can pick any numbers in there for x. Like I actually don't have notes for this. I am winging this video as I'm recording it. I just picked some numbers that I thought would be good numbers to pick. You can pick fractions. You can pick decimals. You can pick numbers that are as big or as small as you want. You can pick irrational numbers. Like you could go and take the square root of 2 and plug it in. So you're taking the square root of the square root of 2. I don't know why you'd want to do that. That would be kind of messy, but you could. There's like no limits to what you can pick. Well, I mean, there are, but like we're going to discover that in a moment. So now we'd have to do some scratch work, okay? And I'm just going to do the scratch work off to the side here and then erase it as I go. I'm not sure how we'll make that look in class when we do it, but so if I have y equals the square root of x and I pick x is equal to 0, well, the square root of 0 is 0. And so that gives me the point 0, 0. If I plug in the square root of 1, well, the square root of 1 is 1. So I get the point 1, 1. And you think, oh, well, the x and y are the same. Now, let's try the square root of 2. This you probably need your decimal for. Now, decimal for, your calculator for. It's honestly pretty late, and it's been a really, really long day when I'm recording this. But yeah, you probably want to grab your calculator. Mathematicians will often leave that as a square root, but for the purposes of being able to graph it, I actually probably do want a number there, at least something that I could estimate what it would be, and that's about 1.414. Okay, and you would go get your calculator for that. So we'll come over here. We'll say about 1.4. Okay, we're going to have to estimate it anyway. Now we've got numbers that are easier to take the square root of. So if I plug in x is equal to 4, the square root of 4 is 2. And so we have the point 42. Then we jumped up to a 9. Again, just looking for numbers that are going to come out nice. We're kind of peeking ahead. If x is equal to 9, the square root of 9 is 3. And so we have the 0.93. Now let's explore the negative numbers. When you're picking numbers for your table, you want to try not to get stuck in too much of a rut with your numbers, because sometimes you need to try different kinds of numbers. So if I take the square root of -1, we know from our study of complex numbers that this is I. Square root of -1 is I, but I can't plot I on the real number line. This is a real number line for the X, and this is a real number line for the Y, and there's no imaginary numbers on the real number line. It's imaginary. And so I'm just going to put in here DNE for does not exist, at least not on the number line. We do have a number system that will deal with it, but it's not anything we can graph. And then with the square root of -4, just as a quick reminder, that is the square root of 4 times -1. And what I'm doing here is I'm doing that quick review of your imaginary numbers. Square root of 4 is 2, square root of -1 is I. And then once again, we end up with this complex imaginary number, and there's no way to graph that. And so on my table, I'm going to go ahead and put DNE there. All right, so there's my scratch work. And now what I have over here is a bunch of ordered pairs. I know that making tables is tedious, but it always works. If you can make a table, you can graph anything. You are never at a loss for being able to construct a graph. So let's go ahead and we'll put a point at 0, 0. We have a point at 1, 1. A point at 2, 1.4. It's true that we do have to estimate that. Okay, 2, 1.4. Yeah, that's a terrible estimate, but A point at 4, 2, 1, 2, 3, 4, and up 2, like right about there. Good heavens, I'm not, oh, just stop. There we go. 1, 2, 3, 4, okay. We have a point at 9, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then up 3. So you can tell it's continuing to go upward, but not very fast. Now, if I come over here to the -1, the graph did not exist. And over here at 1, 2, 3, 4, at -4, the graph did not actually exist over there. And that's going to get into the domain. The reason I wanted to look at that was because we're going to talk about the domain of these functions and what happens, like you plug in the number and it doesn't exist. Now remember, with the table, I can pick all kinds of numbers in between 1 and 2, and in between 2 and 4, and in between 4 and 9. I'm not really restricted to these numbers. So there's a lot more dots in there, like lots and lots and lots and lots and lots more dots that we could have picked, but we didn't. And the way we represent those dots is with that solid line. And so this graph continues to go upward and it continues to go to the right, but it does not go to the left, and it does not ever turn around and head back down. As you put a bigger number under the square root, you're going to keep getting a bigger number for y. Now, that graph there, if you're wondering, like, what on earth is that and how is it connected to the parabola, it is actually the top half of a sideways parabola. That is actually what it is. And so we know a quadratic gives us the graph of a parabola, and a square root function gives us the top half of a sideways parabola. So that's the graph of the parent function. It starts at 0, 0, and it goes up and to the right. So for this next one, we're going to do the square root of x, and then we're going to add a +2 to it. So I want you to kind of notice what that does. If we look over here at this table, if we add the +2, we'd actually be taking +2 of everything in that y column. And I'll show you. So if you've got y equals the square root of x plus 2, and you plug in the 0, well, you've got y equals 0, which was the original number, and now we're going to add 2 to it. And so we end up with the point 0, 2 instead of the point 0, 0. If I plug in a 1, we'd have y equals the square root of 1 plus 2. The square root of 1 is 1. And now I have 3, which is 2 more than what I had over here. So instead of 1, 1, now I have 1, 3. And that's just going to keep going. So once you recognize that that's what's happening, we don't actually need to do all those calculations out. I can come over here and say, all right, when I plug in a 2, I'm just going to add 2 to this. So instead of 1.4, it will be 3.4. I plug in the 4, and instead of getting a 2, I'm going to do 2 plus 2 and get 4. When I plug in the 9, instead of having 3, I'll have 3 plus 2, which is 5. And then, of course, the -1 and it's not letting me do that line, and the -4 are still going to be D and E. Okay, make sure I didn't accidentally pause that. Okay, it's not letting me write the -4 because it's too far down in the corner there. And you can kind of notice now that that pattern is there. And so if you think about it, what we did was we kept all the x's the same, but we raised all the y's by 2. And what that is going to do to our graph is it's going to take our graph that we had, and it's going to shift everything on that graph up by 2. And that hopefully is familiar to you. 1, 2, 3, 4. 1, 2, 3, 4. Okay. And then 9, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5. You guys can't see me, but I'm counting. And there's our graph. And what I want you to notice about that is that it went up 2, which should be familiar to you because we've done that before. When you add a number on the outside of the function, it goes up 2. And what I'm hoping that you recognize is that there's a connection between the plus 2 in the equation, the plus 2 that happens to the y values, and then the upward shift. When you change the y values, that's your y-axis, your up-down, it's going to slide the graph up. So it all does eventually make sense. It should all connect. The graphs, the tables, the equations, they're just different ways of showing the same thing. Okay, now we know from our experience before that a negative should flip the graph over. We're actually going to look at 2 different versions of a flip. It's going to be the first time this happens. I'll actually work a couple of these out though. We'll pick the same numbers. We had some pretty good numbers going on there. So 0, 1, 2, 4, 9, -1, and -4. And we'll do our scratch work over here. So if I have y is equal to -x there, and I'm going to negative square root of x. I'm going to plug that in. The square root of 0 is 0. And -0, that's like kind of silly. That's just 0. So that point didn't change. We're still at 0, 0. Now I plug in the 1. Well, the square root of 1 is 1, and so I end up with -1. And so now instead of having a positive 1, now I have a -1. And if you think about that on your graph, instead of being up here at +1, now it's down here at -1. Let's take a look at the 2. Well, the square root of 2 is 1.41, and so now I have -1.41. Instead of being up here, now it's down here, and you can almost see the flip happening. You can see that flip happening in the table there. Negative square root of 4, well, the square root of 4 is 2, and so instead of a +2, we now have a -2, and I'll illustrate it again. If you're not watching the screen, make sure you're watching the screen. Instead of being up here at the +2, which is what we had before, now we're down here at the -2. And so pretty much every single point that was like up here is now getting mirrored down there. You're getting the negative of it. We have just a couple more to do here. The square root of 9 there is 3, and so we have a -3. And let's check out those negative numbers, okay? That's like important. The square root of -1 is I, and so I end up with -I, and that's still a DNE. We still cannot graph that. And I'll just kind of put the -4 in. And we end up with -2i, and it's still a DNE. Okay, so let's like plot these points and see where they are. If you can plot points, if you can build a table, plot the points, you can graph anything. We have 0, 0. Now 1, we have 1, -1, where before we were up at 1, 1. Now we have 2, and then it's -1.4. And before we were up here at +1.4. 1, 2, 3, 4 down to -2, or before we were up there, and you can see the mirroring. You can actually see that reflection. So it's not, where's my 9? 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we're down 3. And of course, we could pick all those points in between. And that's what our graph looks like. And then once again, we don't have any graph over here. Okay, it doesn't exist. And what I want you to notice was that that was a flip over the x-axis. So there's my x-axis right there, and we just flipped it. Again, if you need to go and watch the video on YouTube, or you need to review this again, just kind of watch this. Like, I really want you to see how the table and the calculations, like what that does to the y value and how that ends up looking like a transformation. Like, these things should make sense. Now, the last one is going to be different. You'll notice that I did the scratch work over here on the right hand side instead of on the left hand side, and this is going to be different. This one actually, we'll pick the same points so that we can be consistent, but this is going to not do what you might expect. Well, maybe it will. I guess it depends on what you're expecting. So let's go ahead and plug in. So now we've got the negative inside the square root. This is actually different. So we need to pay attention here. So when I put the negative inside the square root, then I have, like, I plug in the 0. Negative 0, of course, is like a 0. That's like stupid. And of course the square root of 0 is 0. So we still have that point of 0, 0. That does not seem, that only moved when we moved the graph up. Okay, now let's watch what happens. Now it's going to be kind of crazy. So I have the negative, and I'm going to plug in x is equal to 1. And now all of a sudden I have I. And so before we had a value there, now suddenly we get that imaginary number. It does not exist at x equals 1. Let's do x is equal to 2. So negative, and then we bring the 2 in. I don't know what that is, but I know it's imaginary. Okay? Like that, this is a DNE. Does not exist. Let's go throw in the 4. So the graph of, or y equals the square root of negative 4. I know that's 2i. That is still does not exist. We have a couple more. You can probably figure out what's going to happen here with the 9. You do negative, and now we plug in the 9. That's going to be 3i, but it's not existing on my graph there. That's not a deal. All right, so now let's do the negative numbers, because that seems like that's pretty obvious that that's not going to work for any of our positive numbers. So what happens if I do the square root of negative, and now I bring in a negative 1? So now I've got the negative that was in the function, that's this negative right here, and now I've got another negative that's coming in with the x, which means I have two negatives. And the opposite of an opposite is the positive. And the square root of 1 is 1. And now suddenly I actually have values for those numbers that were not giving me values before. Let's try this with the negative 4. So that would be the opposite of 4, which would be 4, and the square root of 4 is 2. And let's just do one more. We're going to add, let's put like a negative, I don't know if it'll let me do a negative 9. Maybe it will. If we put in a negative 9, I just want to try to get a nice graph here. So I put in a negative 9, and of course the opposite of the opposite is a positive 9, and I get 3. So now let's take a look at what this does graphically. So we're going to plot our points. If you can plot points, you can graph anything. 0, 0 is still on the graph. Now all my DNEs are actually over here. None of those positive numbers worked. But now I've got some negative numbers. So I've got negative 1, 1. I've got negative 4, 1, 2, 3, 4, 2. I've got negative 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 3. And remember, all of these points used to be over here. And now they have been mirrored over here. And of course, we could have picked a bunch of other points. We just didn't. And now we have that. And so to kind of summarize what's happening there, that was a flip over the y-axis. So unlike before, we actually have two different kinds of flips. We don't really see flips over the y-axis with absolute value and quadratics because they are symmetric over the y-axis, and so you can flip them all you want, but they flip right onto each other. But the radical function is the first one that actually is not symmetric, and so we have two flips. So now it's not enough for you to just say it flips. You actually have to tell me if it flips over the x-axis or if it flips over the y-axis. So let's summarize this. We'll go with some lined paper for fun here. All right, here's our summary. And some of this is going to be the same as what we've seen before. So I'm going to do this. I'm actually not going to do, I got to be really careful with this. Okay, I'm going to do this, and then I'm going to introduce one other thing, and I don't want to get it too tangled up, okay? So this should look a little bit more familiar. If you have a negative out in front, it does flip it, but now you need to be specific that it flips it over the x-axis, okay? Before we would just say, oh, it flips it. But now we have to make sure we're indicating which flip it is. Now the A value, as before, this is going to control your stretch or your compression. It's just really hard to draw it. I could demonstrate it for you on Desmos. And if we have time, maybe I can do that and I can show you what like a stretch looks like, a stretch and a compression. But it's hard to see. If A is greater than 1, it's going to be the stretch. Okay. If A is less than 1, it's going to compress. Yeah. Okay. Now the H, this is what's the inside number. And we didn't do an example with this, but we could maybe do one on Desmos. We can do one a different way. We just don't want to keep building tables. This controls your left and right. If it's positive, it's going to slide the graph to the left. If it's negative, it's going to slide it to the right. And we could have done one. I just opted not to. I did this one, and I did this, and I did the negative in front, which I'll address in a second. I just didn't want to do too many tables because this lesson's already getting kind of long. And then the number on the outside, if you're adding, you go up, and if you subtract, we go down. And so that is all the same as what you've seen before. Now, here's what changes. If you have a negative on the inside, this is going to flip it over the y-axis. So the negative on the outside is a flip over the x-axis. A negative on the inside is a flip over the y-axis. Now here's why I didn't put it all together in this, okay? If you have a flip over the y-axis, it messes up your left and your right shift. Because what you have to do is you actually have to factor the negative out of whatever that expression is. And I'll show you real quick what I mean by that. If you had this, you might think, oh, it flips it over the y-axis and it goes left 5, except it doesn't. It goes to the right 5. Because what you have to do is factor the negative out so that the negative is actually in front of the entire expression. That throws off even my college algebra kids. They will look at that and they'll be like, whoa, wait a minute, because it just doesn't do what you expect it to do, and it's got this little catch to it. I am not going to try to trick you with that. I am aware that it's like one of these like really tricky things. So for this class, here's the deal. I will either give you a straightforward problem like this that has the transformations the way that you remember seeing them, or I'll do this where I'll give you the flip over the y, but I won't combine it with a horizontal shift. I might do this. I might put the vertical. The vertical doesn't affect the vertical. But I won't combine the flip over the y-axis with the horizontal shift because I know that that tends to be just like problematic. So I don't want you to worry about it, but I did want to show it to you. All right, so that's our entire lesson on graphs of square root functions, and we will take another whole class period and we'll just practice with these transformations.